So we talk about the various terms relevant to a general tree, the terminology. And let's now talk about how you can construct a tree from scratch. So you ought to know about the definition for what a general tree is. Let's now go over that and see some simple applications, and then we'll move on to Java. And by definition, a tree is simply a set of nodes, but somehow you have to organize the nodes at different levels. But how exactly do we construct the different levels? That will be the question. Right, you want to make sure all the nodes satisfy the parent-child properties. So whenever you got parent-child relationship, that means you got one node that's above the other one. And we got two cases over here. Either the tree is empty or the tree is actually non-empty. And we're going to talk about different cases quickly, right? And then we're going to move on to the applications. Let's now take a look. Right, so I'm just going to try to give you ideas about how you can construct the simplest tree possible. Right? In terms of the root and size, it's always something we want to pay attention to. The simplest tree you can really construct would be simply empty tree. So that'll be case number one. So case number one would just be empty tree. In which case, you can simply just use like an empty set because we got a set of nodes and it's simply just empty. No nodes are actually in the tree. That's one way to represent it, or you can simply say the root. It's a little bit more OO way of tracing the tree. You can say the root is simply pointing to maybe null over here. Either way is okay, right? Just simply no node in the tree. In that case, the size will just be equal to 0. And you can think about that'll be the simplest tree you can have. And normally it would be the base case, one of the base cases for your recursive algorithm on the tree. Okay, that's case number one. What about case number two? So case number two would be when you actually only got the root in the tree. Well, if the tree is not empty, that means you got at least one node, in which case that will be the root. So that means you got the root. Actually, it is pointing to some node. Let me just represent the node like this. We'll try to elaborate on exactly what the structure is like when we go to the Java code. Right? So the root will be pointing to some node storing something. It could be storing some name. For example, Alan. Right, pretty much like the head, or pretty much like the head node in the case of the simply linked list. Okay, in that case, the size would just be equal to just 1. Right, so these are the two base cases that you always want to watch out for. And the third one is actually going to be the more like a recursive cases. You want to know how you can really create a more sophisticated general trees recursively. Let's see, have some general principle. Okay, so I'm going to say case number 3. Right, you can think about this more like a recursive case. Recursive case. And let me visualize that. So basically you have the root at least, but you got the size will be, so what we're talking about here is size actually larger than 1. That's what we're talking about, right? So the root is actually going to point to some node. And then you're going to say the root, this node here actually got a list of child nodes, children, right? So you can think about this one here, maybe simply pointing to an array over here, conceptually, right? And the array, each one of them is going to be storing some reference to some other nodes over here. So this might be pointing to the first child, and also the second child, the third child, and etc. Right? The child indices will be 0, 1, and 2. Right? And now this is where the recursion will actually come in. You should really think about, in this case, think about this will be the subtree. Usually I'll use a triangle to really represent a subtree. And for this particular subtree, the root will just be the first child. So it's really the subtree rooted as the first child of the root, right? And this particular subtree can be arbitrarily complicated, which means the first child over here might just contain further children over here. And each one of them will just contain further children as well. So that's why I say it's recursive. You might just go as deep as you need for your application. Right, so this, let me just write it down. And over here, so this will be the subtree rooted at, you can think about root dot children. In this case, let's assume it's an array at index 0. right? It's a little bit like an informal sketch, but we'll see exactly how to define this coding wise. Okay, and let me just say one more. And you can think about this one over here is simply just another subtree over here. So this will be the subtree rooted at the root dot children at index 1, right? You can see the root pointing to the root of the tree over here, the root pointing to the root of the tree, and then which is an array of children over here. Each one of them is going to be a node, and starting from there you just get arbitrarily complicated subtrees, as many as possible, depending on how many children this particular root has. All right, and what about a parent-child relationship? And for any two nodes you can find, for example, this first child and also this root over here, so you always got the child and the parents, right? That's also something we spoke about before. You can, this one will be the child, and this will be the parents, right? It's only like a conceptual sketch, but I think what you really want to get used to is to think about whenever you want to design recursion, want to think about starting from this particular node, there might be simply some arbitrarily complicated subtree that should be drawn like this. So you want to feel comfortable about calling recursion on the subtree. That's something we'll see maybe more and more as we go over other more advanced topics about the trees. All right. Right, so that's about a very quick walkthrough about, in general, how you can construct general trees, starting from empty and to a one-node tree, and also a tree with arbitrarily many nodes. All right, let's now go back to the slides. All right, and that's simply just about like a legal versus illegal organization for the nodes in the tree, right? These will be legal. You always got a single unique path to any nodes in the tree. That's actually how you calculate the depth, right? In order to really calculate, for example, the depth of this particular node, there's only one unique answer, which will be from the root over here to this node specifically. What about illegal? For example, let's say here, if you talk about this particular node over here, there are more than one path to actually go to this particular node from the root. You can see either you go path number 1 to the left, to the right, here to the right, to the left, right? Even though the depths are the same, but if you got more than one unique path to actually go to the same node from the root, in that case, it will be considered as illegal. And this one here is so-called cyclic, because you can see you can go from, you can go to this node either just directly to the right, or it can be 1, 2, 3, 4, and 5. It's more like a cycle, right? So these two are just examples of illegal organization for the trees. They are not qualified to be a tree, but they're qualified to be a graph, which, if time permits, we'll talk about some introduction to the graphs in this course as well. But for now, let's focus on the tree. Right, let's now talk about some applications about the trees, and we got two applications over here. One is where the children are simply ordered, meaning that the ordering of the children of the each node matters, and the other one is otherwise. The order of the children doesn't really matter. Right, let's take a look at two examples over here. Right, so in the we got ordered tree and also we got unordered trees. These two categories, right? This one over here will be order trees, because if you look at the children at any level, for example, if I look at, let's say this one here, if I look at these are the two children over here, so these are representing, well, the whole tree is representing the table of contents of a particular book, right? And then if we look at the children at any level, so these are simply just the sections, individual sections under a chapter. In that case, of course, the order will matter. Right? In this case, we gotta go to 1.1 before we can go to 1.2, and then before we go to 1.4. So the following section may depend on the previous section, right? So here, the order does matter. The order of child nodes matters. On the other hand, let's take a look at the second example over here. Let's say we talk about maybe the directory structure of your red account in the EECS server. So in that case, under that, you may have maybe one course for CS 2030, maybe another course for 2011, something like that. So Typically, in this case, the order in which you organize the subdirectories does not really quite matter, right? You can think about this particular subtree stores all the contents of this particular course, and this particular subtree simply store the contents of just another course, right? That's really the idea about subtrees is also very important. But if you look at the child nodes, for example, let's say this one here, and this one here got homework number 1, homework number 2, homework number 3. In some way, when you actually try to store the contents of these 3, the order doesn't quite matter, because you don't necessarily have to always access this storage over here before you can access this, because presumably these 3 storages may just be independent of each other, right? Of course, there might be some exceptions depending on how you interpret the application, but I would say in this case, it doesn't really quite matter. Okay, so over here, the order of children doesn't quite matter. Child nodes does not matter. It's a very quick illustration about the two notions of ordered tree versus unordered trees, right? You can definitely think about other examples as well. Alrighty, so now we are done with the basic introduction to the general trees, and let's now take a look at how we can implement a generic general tree in Java.